last time we started section 6.3, and we actually left off in the middle of talking about exponential properties. And we had talked about all the properties, but we hadn't actually done any of the problems yet. So we should be on example 6. Does that sound right? Yeah? Okay, good. All right, so as we're working through these examples, you need to show me something when it's appropriate to show me something. So I realize some of them you can probably do a little bit of work in your head, but you're also more likely to make a mistake if you've done it in your head. So I would encourage you to show me something. There are often more than one way of doing a particular problem. For example, on this one option, the one that I tend to go with most, is to move anything that has a negative exponent. So if it's a negative exponent in the denominator, it moves to the numerator. A negative exponent in the numerator, it moves to the denominator. So if we do that, the a will stay, the a cubed will move up, the b to the fourth will stay, and the b squared will stay. And then a, which is understood as a to the first, would be a to the first and a cubed, which gives me a to the fourth. We add the exponents. And then I have 4 b's on top and 2 on bottom. So 2 of those will cancel, right? Because I have 4 on top, 2 on bottom, leaving me with b squared on top. I'd like to mention another option, not because these are just the only 2, but it's another sort of common option on how to think about this one. What you could do instead is you could think about this in terms of subtracting exponents. So the a value is to the 1, and then we subtract what's in the denominator, which would be subtracting a negative 3. My b value has an exponent of 4 on top and minus the 2 that's on bottom. So if we think about this way, a to the 1 minus negative 3, or 1 plus 3 is a to the fourth, and then b to the 4 minus 2 would be b squared. So obviously we still get the same thing, but we're thinking about it with a different mindset, and that's okay. On part B, we're actually taking a look at a problem that has some numbers in it and not just variables. Our goal is not to try to find a fully multiplied out version of this. That's not the goal, okay? So we're not trying to do that. We're trying to combine things into a condensed exponential form. That's really what we're doing. But the difference on this one, as opposed to, say, the last one, is that I can't combine the 2 to the 5th and the 4 to the 25th in that form or their exponents because they don't match perfectly. Right? The reason that I can combine the a to the 4th or the a to the first and the a to the negative 3 is because they both had base of a. So in order to make this one work, I need for this 4 to the over 25 to actually be written in a form that looks more like 2 over 5. And I do have the ability to do that. So the 2/5 is going to stay to the power of 3. But how can I rewrite 4 so that it is instead have a base of 2? I'm probably not asking the question really well. What I'm trying to get you to recognize is that 4 is the same as 2 squared. Okay? Can you do the denominator in that same way for me? It would be 5 squared, right. So this is where we are right now. And I'm going to shortcut a step right here and actually just pull this square to the outside like this. So I've got double parentheses around it. The 2 is an exponent and the negative 6 is an exponent. Now they do have the same base. There's 2 to the 5th and 2/5 and there's 2/5. They do have the same base. But let's deal with combining these two next. How can I combine those using my properties of exponents? What operation will I use? Right, we'll multiply. So 2 times negative 6 would be negative 12. So now I have a single base to a single power, same single base to to a different power. How can I combine these expressions together? What will I have to do with those exponents? I add them. So now I have positive 3 and negative 12, which gives me a negative 9. Now, we're actually almost done, but anytime we're working with exponents, we're never going to leave an exponent negative. So we talked about how we get exponents to not be negative. We actually did one a minute ago where it happened to be negative in the denominator. We simply pulled it up to the numerator. This time there's a whole fraction that's negative exponented. That's not really a phrase, but we'll pretend like it is. And it means we can actually just flip it upside down. So the 9 will stay 9, but we will lose the negative because we're doing the flip. So this is 5 halves now to the power 9. And again, our goal is not to sort of figure out, okay, now what's 5 to the 9th and what's 2 to the 9th? That's not what we're doing. We want it in simplified exponential form. So we're done at that point. You could write it if you wanted to. I mean, it has sort of an alternate 5 to the 9th over 2 to the 9th. That would be fine, but you're not trying to multiply it out. Okay? Any questions on that? Okay. Let's take a look at a different way that we can utilize our properties. So on problem number 7, example 7, what we're asked to do is to actually solve for the variable n. So on the left-hand side, we have 2 to the n, and we have 2 to the 7th, and they're being multiplied. So how can I combine those in a condensed way? What was that? Close. It's a 7. It might not come through very well. It's a 7. Yeah, n plus 7 is the exponent. Yep. And it's equal to 64, but 64 is not very helpful, at least not the way it's currently written. What I really want it to have both sides written to is the same base. So I really want this written to 2 to the some power that gives me 64. So you're welcome to take your calculator and to try things, right? Try 2 to the 5th or 4th. Try 2 to the 8th. Try 2 to the 6th. Try different values with powers and see if you can find which one is actually equal to 64. This isn't the only way to do it. You could break it down, but it's simple enough, I think, for us to kind of do a guess and check thinking. Do you know what it is, Caleb? I believe it's 6 as well. Does somebody else check that one for us? 6? Cool. So there's a 6 right here. Okay, so exponentials have this property where if they have the same base, which these do, right? They're base 2 on both sides. The only way they're going to be equal is if the exponents are equal as well, because the bases are equal, right? So what this actually reduces to is only comparing the bases' exponents together. That is the n plus 7 and the 6. And you can probably tell me what n has to be just looking at it at this point. If not, feel free to go ahead and do the subtraction of the 7. But what would n have to be to make this work? Yeah, negative 1. It would have to be negative 1. Is that all good? Okay, let's try one more. This one is quite similar to the last one in the way we think about it. However, it is an inequality. It does have that less than or equal to sign instead of just an equation with an equal sign. The left-hand side is already in a very nice form. It's 3 to the power n. So there's nothing I can do on the left-hand side. But my goal, much like the last time, is to rewrite this so it's 3 to some power. Now the first thing you might sort of recognize is that the 81's in the denominator. So if I pull it up to the numerator, my power is going to be negative, right? Because I need my 3 to be in the numerator location. So what I really want, though, is I really want 3 to some power that gives me an 81. Let's break this one down. What does 81 factor into? 9 and 9. And how do 9s factor? Yep, 3s. How many 3s? 4 of them. So over here, this is 3 to the negative 4th. And again, it's negative because the 81's in the denominator. If the 81 were in the numerator, we just have 3 to the 4th. So just like with equations, if the bases are the same, which they now are, we're only comparing the exponents. Well, this exponent on the left is n, and the exponent on the right is a negative 4. And the sign simply stays the same between them. So n is less than or equal to negative 4. Any questions on the exponential comparisons and equations and inequalities? Okay. The next problem we're looking at is an approximation type problem. While it might in fact be true at times that I would ask you to actually find this answer exactly, and I think that you could do that, It's often a good idea before you start a problem that's really messy looking to have in your mind what you kind of expect the answer to be like when you're done. Because if you get the answer when you're done and it seems very unreasonable based on your earlier projection, you might find that you've made a mistake and you're able to catch it. So this is sort of the premise of why we would want to think about this particular problem as an approximation problem. Even if the directions said to find it exactly, we'd kind of like to know what the answer might look like if I approximated it. So if you think about these particular numbers, 20 and 1/3 and 9 and 7/8, they're each close to some other nice value. 20 and 1/3 is really close to 20, right? I mean, it's really close to 20. All right, we're approximating. 9 and 7/8 is really close to 10, yeah? Now I realize one of them we rounded down and one of them we rounded up. So I mean, I get that we're not exactly rounding them at the same level of accuracy, but we're just trying to ballpark what our answer should be if we try to do this. And of course, 20 divided by 10 is 2. So if doing this division, we got something like 1 and 8/6, or 1 and 6/8, we'd be like, oh, well, that's pretty close to 2. But if we got something like 10 and 12/13, we would be like, okay, that's really far away from 2. Something happened and I need to go back and check my work, right? So this answer is approximately the number 2. And then our last two questions in this section have to do with that section C type problem, where it's either an application or a connection to the material in a slightly different way. So in example 9, we have Jasmine. So Jasmine is reading a book. She has 1/4 of the book left and has read 246 pages. How many pages does she have left? So you might sort of imagine that Jasmine is working on some kind of a book where she's reading a digital copy. So a lot of times when you're reading something digitally, like on a Kindle device or on an iPad device, you don't see page numbers the same way. You just see like a virtual bar of how far you're progressed along with the book. That's kind of the idea here. So we know that Jasmine has 1/4 of the book left, and we know that she's read 246 pages. So our goal is to set up an equation, something that compares the two quantities, namely the number of pages compared to sort of it's not really the percentage, but the ratio of the book that she's read or hasn't read. And that's what we're trying to compare. Now, you might look at this, and I hope you do, because you should be careful to catch this and recognize that one of them talks about how much she has done, and the other one talks about how much she has not done. Did you catch that? The ratio part says that she's got 1/4 of it left, right? That's how much she's not done is 1/4. But the page number says how much she has finished, the 246 pages. So we need to decide, do we want to talk about how much she's done or not done? Which is the easier approach? Probably done, because I know a concrete page number and I don't know how many pages are in the whole book, so I don't know how many pages she's not done. In fact, that's what I'm trying to find, right? So I know she has done 246 pages. And while I know she has 1/4 of the book left, I am able to figure out how much of the book she's read in a ratio form. How much of the book has she read in a ratio form? 3/4. So this is my comparison, and it's 3/4 of the total number of pages. So my X here, and you can use whatever letter you want, but this is representing my number of pages, and it's total, like the total number of pages in the book. Now that's not exactly what the question asked. But if I find that information, I can then find what the question asked. So we've looked at a problem similar to this and solved something like this in our last class session together. How do I isolate or get the X to be alone? You got it. So I need that 3/4 to be eliminated. So I can multiply by the reciprocal to do that. 4/3, the multiplicative inverse. So on the right-hand side, I'm left with X. And on the left-hand side, you're welcome to grab a calculator if you would like to do that. We need 246 times 4/3. What'd you guys get? 3 what? Yes, 328. So there's 328 what? Total pages. So go back to the question that we're asked. What are we actually asked to find? How much she has left. So how can I find how much she has left now? Yeah, I can subtract the 328 minus the 246 that she's read. And how many pages does she have remaining? 82. There are 82 pages that she has left to read. Now, the question could have just asked us how long is the book, right? And then we wouldn't have to do that last step. So just pay attention to what the question asks, because there's lots of questions that could, end the question here. Like, that's always a possibility. All right, I really like number 10, because it sounds just like something kids would do. So we've got Al. Al gives 1/2 of his marbles to Jose. Jose gives 1/2 of his marbles to Isabel. Isabel gives 1/2 of her marbles to Letitia. If Letitia was given 4 marbles, how many marbles does Al have now? So this is showing up in this section of material because we're halving things. This idea of repeatedly doing this multiplication of 1/2 over and over again, that's why it kind of shows up here. But it almost feels like something kind of that should show up in, again, I know not all of you have had it or before, but in our number theory portion of the book back in the problem solving chapter. It feels like those kind of problems as well. So I think there's lots of ways that you can solve problems. This one seems to lend itself very nicely to creating some sort of a table or a flow chart of what's happening. So in other words, let's get our kids in order. Al starts out the whole giving of marbles to everybody. And then Al gives so many to Jose, right? EA. And then Jose to Isabel. Then Isabel to Letitia. Is that all my kids? I think so. And the actual thing that we know, concrete, is how many Isabel has when she's done. So how many marbles does Isabel have? 4, right? Isabel has 4 marbles. And presumably, because of the way it's structured here, all of them were given to her by the previous person on the list, which was Isabel. So if Isabel gave her the 4 marbles, and that was 1/2 of what she had, then how many marbles did Isabel originally have? She originally had 8, so now she has 4, right? So this was her original 8. Originally she had 8, now she has 4. But she got her marbles, all of them, all 8 of them, from Jose. So how many marbles does Jose have now? He has 8, but that means he originally had 16. And those 16 marbles then came from Al, which means he gave 1/2, so he has another 16. So he had 32. So this is sort of the structure of what's happening as we're working along the way. So the way that I've written the information down, which is not anything special and you could do it differently, is that we had the 32 to start with, 16 to start with, 8 to start with, and Letitia had none to start with, right? But we should also be able to see right here what they have to end with, right? 16, 8, 4, and 4. And we need to make sure we answer the question asked. How many marbles does Al have now? And he has 16. Al has 16 marbles now. Any questions on that one? All right, so this section is completed. We'll do the 6.3 homework and group work and plan on finishing those to be turned in on Wednesday.